Knowledge about this topic is important as both talk about arguably one of the most important inventions in our history, the pulleys. Many of the machines we see today utilizes pulleys from big planes to small bicycles. But angular and linear velocity don't just explain how pulleys work. Even in astrology, angular and linear velocity has a big impact. It can be used to calculate how fast an object rotates around the sun. With these things in mind, the knowledge about angular and linear velocity is vital in today's age.
For the problem, the two pillars in motorcycle have the diameter of 15.20 cm and 10.16 cm respectively. The bigger pulleys rotates 178 times in 1.5 minutes. In this problem, we need to find the linear velocity of the bigger pulley in minute per second and the angular velocity of each pulley in radians per second.
To do this, first we need to determine the givens. A diameter of 15.20 cm and 10.16 cm for each of the respective pulleys, and the bigger pulley has a rotation of 178 times in 1.5 minutes. We need to also convert the givens to what is needed with the problem. Dividing the given diameter to half to get the radius and converting it to meters. We have also conveyed the rotation of the bigger pulley into radians and the duration of the rotation into seconds.
Next, we list the formula needed with the problem. After listing the needed equation, now we can proceed with the solution.
With all the needed information prepared, solving the problem is quite easy. To get the linear velocity, we just need to substitute it with the given equation, simplify, and we arrive at the 0.94 meter per second.
Next, to get the angular velocity of the both pulleys, we must first get the velocity of the bigger pulley as well. We have all the values we need to get it in. Again, just substitute the given with the formula and we could easily get the angular velocity of the bigger pulley, arriving at 1242 radians per second.
Now, for the tricky part of this problem, we need to get the angular velocity of the smaller pulley with the limited values we have. To do this, we need to assume that the velocity of both pulleys are equal as they are together in the same mechanism. Knowing this, we could easily infer this formula, where the angular velocity multiplied to the radius of the bigger pulley is equal to the angular velocity and radius of the second pulley. A little derivation later, and we arrive with this, where we can easily simplify the problem and get the angular velocity. And in doing so, we got 18.58 radians per second as the angular velocity of our second pulley.